Everybody. So here we have today some setup material to help you kind of figure out how to do this lab that we're going to do. And in the lab, your job is going to be to use some very simple equipment, tuning forks, to calculate the speed of sound experimentally. So that's kind of a cool thing to be able to do. So a couple things you need to know in order to get this lab. Number one, the main kind of theoretical idea that this lab is based on is the concept of resonance, that particular wavelengths will resonate on particular length strings or in particular length pipes. And so today we're going to use pipes to make some resonant frequencies to it. And I'll demonstrate how we're going to be able to use this kind of little apparatus right here to be able to create a variable length resonator so that we can use different length tuning forks to go with each one. So first of all, I want to make sure you can have a chance to kind of hear what these different things sound like a little bit. So I've got three tuning forks here. I've got 256. This is my longest tuning fork, low pitch. So there you go. And then I also have a 384, I believe. Yep, 384. There you go. Little shorter, little higher pitch. And then my last one is a 512, pardon me. So all three of these, you can kind of see how different they are. All right, there they go. Ta-da, 1, 2, 3. They're a little bit, helps me not drop them. But they're a little bit different lengths based on which ones they are. So there we go. There's three ones. There's a short, medium, and a tall. I'm going to be using this one today for the most part, just as a demonstrator to be able to kind of see what we've got. So we're going to use this thing and we're going to resonate it in this tube here. This is actually a piece of PVC and it's on a stand. So I'm going to kind of angle it down real quick so you can kind of see what that looks like. There it is. So it's on a stand down there. And I just have a meter stick hooked up next to it. And then you can see next to it, there is in here a little kind of a weird little tube sticking out of the side. And the purpose of this thing is to be able to give us some indication of what's going on inside the tube, because this tube is actually full of water. It's actually full of water to that level right there. You can kind of see it on that little tube right there. See the little water line that's on there? And what that allows us to do is to have a resonating tube that's this long, basically. There's a water level here, and then it's open from there up. And so that's the length of my resonator. And if I take another piece of tube, like this one, and set it inside the first one, now I can have a resonator that's variable length. So you can see where the bottom is as I put this thing in here. This thing moves up and down just a little bit to give me an idea of where that water level is. Otherwise, I wouldn't be able to see it, right? And then I can make this different length. So that would be a much longer resonating tube. And I've got my meter stick next to it. So all I have to do is be able to kind of do the readings off of here. So I can kind of figure out where the water line is. And I just look at my meter stick. And then I look at the top and figure out what the exact height is. I'm going to angle this back up for the rest of what we're doing today. And so that would allow me to see exactly, how tall is my little resonator on there. I'd just be able to kind of like read it directly off the top. So what we're going to do here is take a look at how resonance works in this different length tube. And I can actually use this tube and adjust the height of it to figure out exactly where this fundamental resonance length is. So I'm going to hit play on this one. Okay. And generally it's quiet. Oops, gotta hit stop here. Generally it's quiet. But there's one height up there that it's particularly loud. Nowhere else does it do that, just at that very top spot. So what that tells me is that right there, that length is going to correspond to, I'm going to kind of try to hold it in place, is going to kind of correspond to the fundamental frequency of this particular tuning fork. So this one's 256. So this length right here resonates with that fundamental frequency, and it actually resonates with a multiple of the fundamental frequency. You better make sure that you check out how these pipes work, which frequencies actually, or which wavelengths actually resonate here. But I would take a look at this and go, all right, there's the bottom of my water level. So that's basically the bottom of my pipe. And then I'd look up here and go, oh, well, there's the top of my pipe. And I'd look across and figure out what those heights are. And that's what I'm going to record in the lab data for you. It will be those pairs of heights. Since I know you guys can't do it for real, I got to do it for you. But they'll record those pairs of heights. You can figure out how long this is, and that'll be able to tell you something about the fundamental wavelength that's able to resonate by knowing what the length of this resonating tube is. So I'm going to do these other ones just so you can kind of see what this is. So that first one I did was the 256, the low C. This second one here is the 384. So I can see I'm still holding this in the position that was at before. Let's see where this one is. So this one's kind of quiet here. Right about there sounds like the loudest, right? Very different spot. And again, we've got a different wavelength, different frequency. So it's going to have a different tube length, a length of the resonator that's going to be able to create that a resonation with that fundamental frequency. And then here's the third one, which is the 512. I'll do it one more time here. This is the shortest one. It's kind of down in there, right? So it's, again, much shorter. So you can kind of see where that water level would be, and then you can see where the top of the tube would be. So you can figure out what that length of that resonating tube would be, or it's actually a pipe, to be able to kind of figure out what this is. And you can use some, basic math, basically at that point, some algebra, to be able to calculate some things about what the speed of sound must be at this temperature, experimentally determined anyway, and you'll be able to compare it to the known speed of sound at our particular temperature. So I want to point out one last thing that's kind of cool about this particular setup. So here's my long one again. This is the 256. So it's got a resonant area kind of right in there. But there's a second one. It's like right about there. Okay, so there's two different spots that I can get on this one, and it only happens with the long one. The other ones, they're just too short to be able to do it. If I had an even bigger one, I could get a couple spots as well. But I had the fundamental up at the top, that length that was up here someplace. Now this is actually the first harmonic, or the second harmonic, I guess if you want to call it that way. But it's the second resonant frequency, and what's kind of cool about that is that one and this one, basically the same. And that is because these two notes are the same pitch. This one is the frequency of 256 is a C, and this little short one that's doing the same thing is a 384, or a 512. There it is. That's a C as well. So those two should be able to have kind of some similar resonant frequencies because they're both the same note. And again, remember, this one, the long one, its first harmonic should be the second one. It's kind of cool. So there you go. This is the basics on how to use a variable length resonating pipe with some different tuning forks and some different known frequencies to be able to calculate the speed of sound. So I will post up lab data for you guys to use, but I wanted you to be able to kind of see the setup for it. It's kind of gross and wet. Yeah. Okay, there you go. See you later, guys. Bye.